Um, Hello, everyone. I'm Junjie from XFEP, and it's my pleasure to be here to talk about our force field, which XFEP and the Pfizer built together. And so you might have heard about XFEP because of a unique capability in crystalline structure prediction. But crystalline structure prediction is not the only thing that XFEP is good at. So as the company growing to a medium-sized company, so we have extended our capability into new areas such as small molecule drug discovery, which is the department I'm currently related to, and also antibody. And more recently, the company has spent a lot of effort on lab automation, especially automated chemical synthesis. So today's talk, I will begin with introduction about the technical detail and the performance of our XFF force field, and also its application in FEP. And I will also talk a little bit about our XFEP platform. And also in the final part, I will share a very interesting study in which we use ABFE to do rescoring of docking poses for fragments. So the development of the force field was started in 2018, and the whole project was initiated by Dr. Junjie Zou, who is here from Pfizer. So XFEP's role is to write all the codes and the scripts for building this force field, and also we carry out large-scale quantum mechanical calculation to get all the data necessary for doing the parameter fitting. And in 2020, we got our first internal version of the force field, and we also built a customized force field for Pfizer, which should better cover their internal compound library, so they can get better results in their own projects. And we also rebuilt the infrastructure in 2023 because we are keeping having more and more quantum mechanical data in our training set. So we found that every time we change a little bit of the van der Waals parameters, it takes us more than a week just to refit all the torsional angle parameters. So in 2020, we put the structure on GPU, so all the refitting can be done just in no more than one day. So the force field has matured in 2024, and we have published the force field in the journal, and it's an open parameter one, so everyone can access that through this website. So this force field, XFF force field, we use Amber format. The reason is that we want this force field to be compatible with any MD simulation engine. And on the bottom, so this table gives the summary about the number of parameters in the XFF force field, and also the size of the training data set we use to fit the torsional angle parameters. And we got the bound and angle parameters by doing the fitting to the QM optimized geometry and the Hessian matrix. And the torsional angle parameters were just obtained through the regular torsional angle scanning. And we borrowed the van der Waals parameter from GAF1, and we use RISP charges for the partial charges. And we also have tried other options for van der Waals and the partial charges. We have tried M1 BCC. We also tried our own empirical partial charges and our self-developed van der Waals parameters. But in the end, we found that GAF1 plus RISP charge is the best for reproducing quantum mechanical energy, and more importantly, it performed the best FEP calculation. So the force field has a huge number of atom types, and all the atom types they are organized in this highly extensive hierarchy structure. So for example, if we have sp2 carbon, so these carbon will be split into different atom types depending on its chemical environment, and we can further split the atom types to sub-atom types depending on whatever criteria you choose. And we also have an equivalence table. So these allow the atom type to borrow part of those parameters from its parent atom type. So it did take out a lot of labor work, at the beginning to just define all the atom types. But we found that once you have done that, that's a one for all thing. So once you have done that, this force field is actually quite easy to manage. So every time you need to add a new atom type, you just go to the hierarchy structure to see where it should go and use the equivalence table to borrow parameters from others. So here's a comparison we have done, a benchmarking we have done on a data set called OpenFF industrial set. So it has more than 70,000 QM calculations. And so we are looking at four different matrices. So the first two, RMSD and the torsion fingerprint deviation, represent how good the force field optimize the geometry, reproduce the quantum mechanical optimized geometry. And the last two is showing the correlation and the error between the force field predicted and the QM calculated energy. So you can see that our XFEP force field is actually doing quite a good job on this data set. So in XTOPI, we've also developed our own FEP workflow with GUI to support the use of this XFEP force field in our own projects. So here's just a quick comparison between XFEP using XFF with Schrödinger's FEP+. So I would say that they have quite comparable performance in terms of R-square and delta G errors. So if you look at the averaged R-square, you can see they have quite similar R-square, overall R-square. But if you look at individual target system, you can see it can be very different. So I think the reason is that so for XFEP, so for both the small molecule force field and the protein force field, we use resp charge to derive the partial charges. And I think for Schrödinger's FEP+, if I remember it correctly, they use more of those semi-empirical partial charges. So that could be the difference for these individual target. And we've done a lot of optimization in our XFEP workflow for those small detail stuff. So a lot of FEP workflows, they use maximum common substructure algorithm to do the atom mapping to find the common parts. But we know that this maximal common structure in RDKit it's not designed for FEP purpose, right? So in XFEP, we have optimized the mapping algorithm. So for example, if we are trying to put a substitution on a benzene ring and make it, which make it unsymmetric. So the best thing to do in FEP is actually not to atom map the whole benzene ring, RBFE calculation. So this will put the whole benzene ring, including its substitution, into the hot region if you are running replica exchange FEP. So the FEP will figure out the correct binding pose for this benzene ring in the simulation itself. So you, with a better binding poses for this benzene ring, we can get better delta G values. And the other feature I like a lot is the per residue decomposition. And I know a lot of people will argue that per residue decomposition can never be done perfectly. And I totally agree with that because free energy is a state dependent, but decomposed per residue energy is pathway dependent. So it could be that the decomposed value doesn't have too much physical meaning, but in my experience, as long as the decomposition are done in a very consistent way, and and if we are used to the behavior of the decomposition, I think we can still learn a lot of stuff from the decomposed value. So in this in this example, we are transforming hydrogen into an amide. So the purpose of the amide is to try to catch a hydrogen bonding with this tyrosine 91. But the decomposed free energy is telling us that actually it didn't form strong hydrogen bonding in the calculation, because in our experience, if the ligand does form hydrogen bonding with the protein, we should be expecting an electrostatic free energy contribution at least more negative than -1. And if we look over here, so the system also reports relatively larger contribution from the van der Waals free energy of the solvent. So this behavior is actually indicating that the addition of this amide caused some penalty of displacing waters. So with this all information, so it's actually quite useful for drug designer to think about whether they want to try again with a new functional group, or maybe we should just leave this site and leave this site alone and not to perturb the pocket water. And also for force field developer, this is also very useful, because it lets you know which part of the system is contributing more to the final delta delta G. So if you have any inaccuracy, probably the inaccuracy is coming from the part of the system that's contributing most of the free energy, right? For this example, it's probably, let's say if anything is wrong, probably the defects is coming from the water and the protein interaction, because it's coming from the solvent part rather than the small molecule itself. So we have a GUI for the whole workflow of our XFEP. So, and it's also available for external use. So in summary, we have built a Amber compatible small molecule force field, and with a broad chemical space coverage. And this force field is open parameter one, which you can access through this website. So you can upload an SDF file and get the parameters in any of the Amber, Charm, or GOMAX format, or you can just go to the website and download the tools and use it offline if it's for academic use. And we have more benchmarking results about our XFEP force field and XFEP. And you can find that in this publication we published last year. And also XFEP, we have built many useful features into it for better interpretation of results and other things. So next, let me go to the final part. So this is a very interesting study we have done in which we want to see the behavior of if we are using ABFE to do rescoring of docking poses of fragments. So there are several studies has shown that fragments. So this one is from ACETEX, so a publication in 2011, and they have shown that docking of fragments is very challenging, and it fails more because of the inaccuracy in scoring functions rather than sampling insufficiency. So that means even the docking program has enumerated a native like binding pose, the scoring function is just not accurate enough to top rank that, especially for fragment sized compound. And this is also this behavior was also seen in a publication in 2020, and this in this study they have published a data set. They selected fragments co-crystal structure so people can use that for benchmarking. So we use that data set to do the benchmarking for ABFE. So I know the comparison is quite unfair. You know, ABFE costs much more computational resource than docking scoring function, right? But the main purpose is to answer the question why ABFE performed better, or why VNAV failed in some cases. So we have done several modifications to the regular ABFE protocol people use to calculate binding free energy. So the first modification is that we don't put, we remove pocket waters in the beginning of the simulation. So this is to remove any bias that caused by the shape of the pocket water. And also we put a heavy restraint on all the heavy atoms of the receptor. So this is to mimic the docking algorithm, because most of the docking algorithm, they will score the ligands in static receptors. And the third modification is that we put, through all the lambda windows, we put a Boris restraint on the ligand. So this is to prevent the self-optimization of those decoy poses during ABFE calculation. So here's the conclusion we have found. So if we look at the difference, so it does. So ABFE does perform much better than VINA docking scoring. And we found out that the reason is that VINA, it fails a lot when the number of hydrogen bonds in the native pose is fewer than 2 or equal to. So so this is expected, because if you look at the functional form for the for VINA's scoring function, so you can find that they only have one. If I remember it correctly, they have one term, just one term for electrostatic interaction, which is a hydrogen bonding term. So it could be that VINA relies too much on the number of hydrogen bonding when they are just because of the simplicity of their functional form. But for ABFE, because it has a more robust description of all those electrostatic interactions, so ABFE is not that picky. You know, it has a more consistent performance across all those number of hydrogen bonds in the native states. And the other things, so we also look for reasons why ABFE fell. So the reason is we found a lot of different reasons. So one of the things that's interesting is that we found that for both ABFE and the VINA, so their performance, their prediction accuracy actually correlates strongly with the quality of the electron density of the ligand. So I must say that the data set was actually prepared very professionally. The author have used a lot of criteria to select those co-crystal structure to form this test set, but they just used the global resolution of X-ray to select their co-crystal structure. And here it's clearly showing that if we want to select co-crystal structure for training or testing scoring function, maybe we should be considering using cutoff for those local resolution around the ligands. So that means so here's the summary. So we have done the comparison using ABFE and the VINA, and we figure out that VINA fails a lot when there are fewer hydrogen bonding in the native binding pose, and a lot of the time ABFE failed not because of the inaccuracy in its scoring ability, but it's more because of those uncertainty in those co-crystal structures. And we have published this study in a preprint, and you can read that to find more examples. And as I think a lot of people have mentioned that FEP has reached an accuracy that it can help people to identify artifacts in experiments. So yeah, so I'm thinking that maybe you can consider using ABFE to validate those co-crystal structures that's deposited in PDB bank. And with all that, I would like to thank my colleagues from XTOPI for their support in all those works they've done. And also I want to thank our collaborator from Pfizer, especially Dr. Junjie Zou, who has give us a great support in doing science and project management. So with that, I would like to take any questions.
Hi, all. Really quickly, just a quick security thing. We have a bunch of people standing here, and we can't have that happen. So this is what we're going to do. If you see a seat to the left of you that's open, fill it. Thank you, guys. Thank you.
The security was fast, you know, you can hear the like I'm talking on the.
Yeah,
Sorry about that, guys. Don't mean to ruin the vibe.
Okay, questions? As you guys are moving, can you ask a question?
Thank you so much, everyone. Oh, wow.
Questions?
Um, so the removed pocket water will come back during the ABFE simulation. So if they have the access to the pocket, so they will. If I remember it correctly, it's 4 nanoseconds for each lambda window. So yeah. Yeah. So I think uh, so our way is just to allocate the final free energy you got in delta delta G into different component. So this is actually I think it's better identifying the source of those contribution. You know, if you do GBSA or other stuff, probably it has some estimation, you know, approximations. So you may lost the source of those contributions if you're using those GBSA method. So does that answer your question? Yeah. So it depends on how many VINA, how many pulses VINA give us. So sometimes 7, sometimes 20. Yeah. But we use all of those in the ABFE calculation. Yeah. What's the question? Mm-hmm. Uh, I think sorry, I might not be able to answer your question because yeah, I think it's maybe have 3 layers probably. I could be wrong, but the thing is that it depends on how many. I think it depends on how many quantum mechanical data you have for training. You know, so for each atom types, we need to make sure there are enough quantum mechanical data that model compounds in your training set to cover these atom types.